In a quest to use Bitwig mostly natively, I wanted to reverse engineer or recreate some of the tools I like to use. One of which is Camel Crusher. I used to use it a bunch, now I sometimes use it, but I still kind of like it, and I figured since it's a distortion, it's probably easy enough to recreate. Except the compressor knob, oh my gosh, the compressor knob, but we'll get to that. I was inspired by this video from 9b0, which explains most of it, but for me to understand it the best, I figured I'll just rederive all of the math myself and do it in Bitwig. So the easiest place to start is the meg knob, which is the following. Boom! We can see that it's rotationally symmetric around this point. We can see this as the origin. We'll run a sawtooth wave through it, by the way, to analyze the transfer curve. This is my version of it. Boom! It's the same. Yay! So it works. So what's happening here is that when it's at 0 and unengaged, the transfer curve is linear, and so nothing happens to the signal. When it's fully engaged, the slope here is 11. Roughly, at least. That's kind of what I found, that what we found, 9b0 found as well. And yeah, it seems to match. And so we'll be deriving that. But first, I derived a general equation for a piecewise function like this, which looks like this. So here we have the graph. We only have to care about the positive part because it is symmetric. The function is constrained by the 0 point, this a point, and this point at 1. And this a point in this general equation is free to move. And so you can pause if you want and look at the math, but the way I like to derive transfer curves like this is to first define constraints, then make an assumption about what the function looks like with some general parameters, and then derive those parameters, in this case alpha and beta, for each piece, and therefore find my final equation. And this is what I would be making in Bitwig. So if we go in Bitwig, boop, this is the meg part. And this part that I'm selecting now is the equation itself, the general equation that was on the screen just now. The only thing, and I'll explain this, you know, I'll just go over this function first. So this is the function that comes in. We take the absolute value and multiply by its polarity at the end so that this whole thing is a symmetric process. I route this to be just easier to see that this is the absolute value in. The first part of the function here is this one. It's AF over AX, where AF is the y coordinate or the f coordinate of this point, and AX is the x coordinate of this point. So this also, if you know math, this just gives the slope, which is what happens here. This is AF, this is AX. We'll get to this part in a minute. This is AX. We get AF divided by AX. We multiply that with our function, with x, and then boom, we have the first part. And then this is the selector, which checks if x, or the input function, but if the input is larger than ax. If it is larger than ax, which was this point, remember, we should switch to a different function, which is this bottom one, right? So and so this bottom one, let's engage the meg for a bit. So the top part is this first half, and then the bottom part here is this second half. So here I just do the math that I wrote down here. AF minus 1, AX minus 1 times x minus 1 plus 1 is just what I found using the constraints, which is all of this stuff. You can read it. And this gets engaged when this check is true. When it is not true, the first piece gets engaged. And so that's how this mostly works. Then all I had left to do was parameterize the knob. So this whole thing is not engaged when meg is 0, and it is fully engaged when meg is 1. As in, it's linear when it's 0, and it's non-linear when meg is 1. As a result, the way I solve this is by multiplying the meg knob by 10, then add 1, such that when the meg knob is fully engaged, we get 11, and when the meg knob is not fully engaged, we get 1. So the slope is 1 when it's not engaged, and it is 11 when it is engaged, which matches Camel Crusher. And with this slope, I mean the slope of the first piece, of this first piece here. Because the second piece just automatically follows from the constraints, right? We don't have to care. Once we know this, we know this. That's what the constraints do. And that's what this bit of math solves for us. So that is the meg knob. And then the next part was the tube knob. Tube is a slightly more complicated one, but it boils down to a similar thing. Let me prepare. So tube, if I go into the oscilloscope, tube does a very similar thing. We have a node and a linear piecewise, and a function with a linear piece first here. It's also symmetric, by the way, so we only have to care about absolute values. But then here it makes like an arc. And this is my solution, and also 9b0's solution, which is close. The first half is exact, the second half is... it's close enough. So the math is mostly the same. Well, the first part is the same, right? Because it's you know, a similar function, except the node is now at 0.6 instead of 0.75. And so if we look at the math here, we get the same first half, right? AF over AX. But then here we get math. So the way I constructed this, and that 9b0 constructed this as well, was to assume the first pass to be linear, blah blah blah, this is solved, and the second half to be a sine. It looks very sine-y. 9b0 used the cosine, but you know, cosine and the sine are mostly the same, except their phase offset. The reason I chose, I think they chose, but at least the reason I chose the sine is because it's horizontal here near the 1 point, which is here. It's kind of horizontal, and then it arcs kind of sine-y downwards. And so I just assumed that the second equation would have that the second half of the piecewise equation would be of this form, some sine form, with 3 parameters. And then I solve for these parameters, and it's a little complicated, but you can pause if you want to actually... Well, it's not too complicated, it's just, you know, arithmetic. It's a bunch of arithmetic. And then I just do the same arithmetic in Bitwig. So this first half is, again, the same. Here's the AF over AX, and then here's the part that deals with the sine. Here's the parametrization. The slope is 5 instead of 11 here. So it's slightly different. But the idea of the parametrization is the same. Multiply by 4, then add 1. So that at 1 it has a slope of 5, and at 0 it has a slope of 1. And with slope here I refer to the first half, since the slope of the second half is variable. But I refer to the first half because that's the one we control. And then the second automatically follows. So the whole method that I used here was just it's the method of constraints. The way I just derived this by setting up my constraints, making an assumption on what the function will look like, and then using the constraints to find some constants and some parameters that I need to construct the function, and then you automatically connect these two, right? So these parts are connected, the first and the second parts, because they're constrained here, right? They're constrained together. I have to make sure that f1 equals f2 at that exact point. And so I just keep doing this. Whenever I derive transfer curves, and like the circle I showed earlier, I do nothing but setting up my constraints, making an assumption on what the function looks like, and solving then for, you know, I make an assumption on what it looks like using constants that I don't know, and then I will be deriving the constants. Like this linear function, I know that it will be some slope times our input x plus some constant, and I just solve for those. That's what I do like all day, every day. And so that solved this, and so I think this is fairly close. It's close enough. I'm satisfied with this. Now fucking the compressor. Let's turn on off the distortion. Compressor is a disaster. It's a nightmare. So if we turn off fat mode, this thing is black magic. So this function, when none of the distortion is engaged, it's not very difficult to derive. As you see in the oscilloscope, it's just the same. It looks mostly the same. Oh no, actually, I'm starting to notice something, but at the moment I can't be asked to rederive this. But at a first glance, it looks like kind of a linear function at first, and then it just flatlines. So it's another one. It's literally, it looks like another one of, Entschuldigung, of this form. But then AF is just put to 1. And so then you move this point here. But then when I engage Meg or Tube, it does like all sorts of black magic, and honestly I couldn't be arsed. So for now, that's the only thing I haven't reverse engineered. Fed mode I have. So well, close enough. So fed mode looks like it's a 2-stage thing. The second stage is awfully close to Tube, right? We have, it's symmetric again, so we only have to care about absolute value. It's piecewise, and we have a linear piece here at first, and then something that kind of, again, looks like a sine function here. And so this was just the same math, but different numbers, right? Different numbers. This is the node is slightly lower, the slope is probably different. So it's just the same, but let me engage compress, but just slightly different numbers. So here I'm close. It's not the exact same, but I'm satisfied. I'm fairly close enough. I'm happy with this. Although I think I can reduce this point here a smidge. My function comes a little too above, and I wanted to try a different arc because it doesn't fully align. The thing about this transfer curve, though, is that it's 2-stage. So this is the second stage, and the first stage does something remarkable. What it does, so if we move the amount knob lower and lower and lower and lower and lower, boom, there's like a point where, like, I think it's at like 0.4-ish. There's a point where, if you see, you kind of see an angle here still, right? You see an angle, which means that the slope of the first function and the second function at this point is not the same. But as I move this knob down, there is a point where you don't see this node anymore. You don't see the corner, which means at this point here, the slope of the first half and the second half is the same. And when this occurs, if we lower this further and further and further, you see how this kind of corner starts moving up. So it looks like the arc here stays the same. Like here it changes because we move the node. But at some point it's almost like the arc doesn't change anymore. And it's just this first half which gets longer and longer. So if we go into the compressor function, it again, it's just the modifier. So this is the second stage, I believe. And now it's fairly, this is fairly simple. The thing that makes it difficult, this one, is the parametrization of the complex knob. The second stage engagement is just similar to the two, but the first engagement, at some point I'll assume that this sine wave, or this, not the sine wave, but the sine function here stays the same. At some point I'll just assume that it stays the same, and then I just do a check here. Sorry, I'm in the wrong node. Then I do a check here to see, is my linear function bigger than the sine function, i.e. does it extend above? When it does, go to the sine function. When it doesn't, go to the linear function, which has as the effect that when I engage this, you see, it doesn't exactly look the same, but for me it's close enough where I'm satisfied. It's like, you know, if you extend this linear function, it would be above the sine. So when that happens, go to the sine. When the sine is bigger than the linear function, which if we extend the sine, that is what would happen, go to the linear function. So it kind of cuts off the sine here. Right? That's the first stage. So we cut off the sine, cut off the sine, cut off the sine, cut off the sine, until we reach some point where the derivative at this point is the same. That is the construction that this sine follows. And then we engage the second stage where we just do basically a modified tube distortion.